Hello everyone and welcome to today's session. In today's session we're going to be looking at calibrating the two motors. If you've not completed the two previous sessions, so if you've not completed your shield yet and you've not completed your motor board, you're going to have to go back and complete those first because we need those working in order to calibrate the actual motors. Please ensure that both your motors are spinning in the correct direction, so when you're pressing the forward button they go forwards and when you're pressing the back button they're going backwards. Please also ensure that your two buttons are working, although saying that, if you've tested your motors from last session, when you press the two buttons to test the motors, they should have worked, so that should all be tested anyway. Just make sure everything is working before we get to calibration, otherwise it's simply not going to work for the calibration. Now, motor calibration is to ensure that both the motors are running at the same speed when we're going forwards and backwards. Okay. Now, what we're going to do, when you have an electric motor, you put power into the electric motor, it's going to spin as fast as it possibly can with the power that you're giving it. It doesn't actually know what speed it's spinning at. Now, when you've got two motors and you're putting the same amount of power into both motors, they may have slight differences in them. So the gearbox might be slightly different, the actual motor wiring, etc. might be slightly different, the magnets might be slightly off. And as a result of which, they're going to run as fast as they can, but they're not going to run at the actual same speed. So what we need to do with our Arduinos, what we're going to do is we're going to set the speed of the two motors. We're going to place the robot down on the desk and we're going to see if it drives in a straight line. If it doesn't drive in a straight line, let's say it goes off towards the left or off towards the right, okay, we're going to adjust the speed of one of the motors until it does drive in a straight line. So we're going to basically speed up and slow down one of our motors. In this case, I think it's going to be the right motor that we're going to change the speed on. What we're then going to do, once we've done that with the Arduino and we've started that calibration and we've got it driving in a straight line, we're going to save it, or those calibration settings, onto your Arduino in a little piece of memory called the EEPROM. This is essentially memory that will not get wiped when we power it off. When we power it back on again, we're going to have a little bit of code that then reads that piece of memory, pulls those calibration settings back in again, loads them up, and then your calibration remains on your little Wizibot so that you don't have to do the calibration every single time. Okay. Now that means we're going to have to introduce this EEPROM, or electronically erasable programmable read-only memory. Now EEPROM is essentially a long line of different evolutions that have happened with the memory, hence the weird long name. Okay, in the early days, I think it was about the 1950s, 60s, we had read-only memory. Okay, these were little chips, and what we essentially did was we wrote to the memory during the manufacturing process of the chip. You could not write to that memory ever again. It was a read-only memory chip, and you had to send it off to the chip manufacturer for them to actually put it onto the chip. What we then had as an evolution of that, where it became a programmable read-only memory. Okay, now the manufacturer made the chip, they'd send you the chip and you could program it the first time. You could do it once and once only with your program. Okay, if you ever got that wrong, you basically, what we call, brick the chip, and you basically have to throw out the chip and start again. Okay, you couldn't erase it again, you couldn't write to it again. It was write only once. After that, obviously that was a little bit of a pain for some manufacturers. We came up with erasable programmable read-only memory, which was usually erased using UV light. So there's a little window on top of the chip. Some really old chips, you might see it, okay? But basically there's a little window at the top there, and if you shined UV light into it, it would wipe the chip out and allow you to write again to that chip. That's obviously quite useful if you want to be able to upgrade stuff, but it all had to be done in the factory by the product manufacturer. Okay, so it's not the chip manufacturer, it goes to the product manufacturer, they erase it, they write the details that they want into it, and then they send it off to the customer. The customer would not change it, and the microcontroller would not change it. It would be read only, essentially, at the end point. Obviously, again, that's a bit awkward, okay, and so they came up with electronically erasable programmable read-only memory, which is the one that we're using today, where we can actually erase it using a microcontroller, so we can send signals to it electronically instead of UV light, and we can wipe it and then rewrite it, okay. Now, obviously, once you get to that point, someone worked out you can plug it into a microcontroller and you can read and write to that chip multiple times, based at the end point, effectively, with the customer. Hence, in today's session, we're going to be writing to the EEPROM, and we can actually wipe it again if we want to at a later date so that someone can do a different calibration on that chip, okay? But that's why it's got such a weird long name, and it's still got the name read-only memory in there, okay? Because it's kind of got that evolution that goes back the way. It's not really that descriptive today of the actual what it does. Effectively, it's like a little mini hard disk, okay? We can read and write to it, we can erase it, and we can do all sorts of other stuff. Now, the Arduino Uno R3s, the ones that we're using, they have 1 kilobyte built into the board. Okay, Now, 1 kilobyte is 1024 bytes. Each kilobyte is 1024 bytes, okay? As a result of which we've got that memory. It's not a huge amount of memory, okay? But it's enough for what we're going to be doing, okay? We're going to be writing basically 2 bytes. We're going to write the left motor and the right motor speed. That's a value between 0 and 255. And 0 and 255 is a single byte, and so we're only actually going to use, I think it's 3 bytes we're going to use, because we're going to have a little header byte in there that just tells us that we have written to it and that calibration is available in the memory. Okay, so we're going to read and write our own data, and the easiest way to think about it is it's a tiny little hard disk that we can use to store information about our programs. Now, memory is stored in the form of bytes, okay, and then we essentially have an address that we store it at. In the case of the Arduino, we're going to have a value between 0 and 1023, okay, because we've got 1024 bytes. 0, 1023 is 1024 bytes, okay. At each address, okay, we can write a value between 0 and 255, a single byte. Now, if you wanted to write larger numbers into there, you can use multiple bytes and use larger variable types. We're not going to do that today, and I'm not even going to go into that today because it's too complicated for the stage that we're currently at. Okay, but effectively what we can do is write our bytes in there, read our bytes out, and then if we really wanted to, we could actually write much more complex data in there if we wanted to. We're not going to do that today. Okay, but the easiest thing to understand is we're going to have a command, EEPROM.write. We're going to open a bracket, we're going to say the address 0, and then we're going to have a comma followed by the value that we want to write in between 0 and 255. So EEPROM.write 087 would write the value 87 into address 0 on the EEPROM. When we want to then read it back out again, we simply say int read value, because we want someone to put it into a variable in memory, equals EEPROM.read, and then we simply give it the address that we want to read. So in the example in the bottom there, we would say int read value equals EEPROM.read2. It would go off, it would read address number 2, which has a value of 150, and it would place 150 into read value, and then it's up to us what we do with that value. Okay, you're going to see that in the code today. If it doesn't make too much sense right now, just bear it in mind in the back of your head, so that when we look at the code, you can try and tally them back up. You can always come back to this slide and see how it works. But the most important thing is we tell it what address we're going to write to, we would tell it what address we're going to read from. Like I say, with the Arduino Uno R3, we have up to 1024 bytes. With other microcontrollers, you may have more or less memory, so just bear that in mind if you are changing between microcontrollers. Now I'm going to break down the program. I'm going to give you the code for the calibration today. It's on the Now Room, you're going to download it, but let's quickly run through how this code actually runs. So you could load up this sketch if you want, and it would look like this. Okay. Now, first thing we're going to do is we're going to ask the Arduino to bring in that EEPROM library. Okay, that's how it's going to know how to deal with the EEPROM. So there's the code basically in that header file that tells it how the read and the write commands work. We're then going to define our pins for the motor board, which we did in our testing last session. Okay, we've got button B1 and button B2 that are going to control the speeds of those motors. And then we're also going to create 2 variables in left motor speed and in right motor speed. These are going to store the motor speeds that we're going to store into our EEPROM as well as load from our EEPROM, okay? Because they're going to set the actual motor speeds, the calibrated motor speeds that's going to allow your robot to drive in a straight line. What we then do is we simply start our serial transmission between the Arduino and the PC so we can see what's going on, should we need to. Okay, and we set up the pins with the pin modes, outputs for your motors, and then input pull up for your 2 buttons so that we can read the inputs for the buttons. What we're then going to do at the very end there, we're going to make a call to our function to read from the disk, or our EEPROM. Okay, that's going to go off to the function that we'll look at in a second, where it actually goes off and actually reads in the memory from the EEPROM. So here we have our function for write to disk. In write to disk, we're just going to do 3 things. Okay, we are going to write in a character, number 87, which is the character W in text. Okay, this is what we call ASCII. Now, the reason why we're going to do this is because when we first boot up our Arduino, we want to know, have we actually set up a calibration, or is it some other random piece of memory that someone's written for a completely different program? If it was a random piece of memory that someone wrote for a different program, the first byte might be at 255, the second byte might be at 0, and the robot will drive round and round in circles. Okay, so we want to know, did we write this? And what we're going to do for that is we're going to write in what we call a header, or a little character, the W, into that byte. Now it is possible that someone does write the character 87 in on their own program and it will mess it all up. Okay, but in this case we're just going to try and do it as a more precautionary step to ensure that we are pulling in a calibration instead of pulling in other random information. The second byte that we're going to write is going to be your left motor speed, and then the third byte is going to be your right motor speed. Okay, so we're just storing 3 bytes in there. The first one is your header, which is just the character W. Okay, the second one is going to be the left motor speed, and the third one is going to be the right motor speed. In the next function, we have read from disk. This is where we're actually going to read it from the disk. The first thing we are going to do is we're going to do EEPROM.read on that first memory address of 0. Okay, and we're going to check, is that a W? Okay, because if it is a W, then it's likely, or most likely, that we did write a calibration onto that memory. It's not just some random information written by another program. If it is a W, we're then going to pull in the first byte with the EEPROM.read1 into the left motor speed, and then EEPROM.read2 into the right motor speed. Okay, now we've loaded it into memory. We've now pulled in the calibration settings that we previously saved into the EEPROM. If that character, that first character that we have, was not the W, okay, we're then going to default at the bottom there in that else statement. We're going to set the left motor speed to 150 and the right motor speed to 150 as the defaults to start our calibration. We want the motors running forwards. We want them running at a steady speed. At this point, it's just the default settings. That's when we're going to set up the calibration. Now notice that once we've done that in this read from disk function, we then write to disk those basic calibration settings to ensure that we have something written in the memory. It's now basically set up and ready to go. Both values are set to 150. It won't be calibrated at this point, okay, but the next step will be to actually run that calibration process. Now let's look at the actual loop function within your Arduino sketch. This is the bit where we are actually going to do the calibration using the 2 buttons. Okay, so the first thing we're going to do in the loop function is simply set the 2 motors to drive in the forwards direction. Okay, we've got a little function at the bottom there, simply sets both the direction pins to high to ensure that both motors are running forwards and neither of them are running in the backwards direction, because we need to calibrate it in the forwards direction. Now what we're then going to do is we're going to check the 2 buttons. The first thing we're going to check is button B2. Okay, if button B2 is pressed, we're going to use that to speed up our left motor. Okay, so I said it wrong earlier. It's the left motor we're going to change the speed on, not the right motor. Okay, so what we're going to do is we're going to check B2. If button B2 is pressed down, we're going to first check are we definitely not above 255, because we can't go faster than 255. We don't want to speed beyond that, otherwise we kind of get stuck in a weird little loop. Okay, so we're going to make sure that it's not above 255. If it's below that 255, we're then going to increase the speed by 1. And we're going to write that new calibration into the EEPROM to ensure that it remembers that new change to the speed. Now what you should see, if you're pressing button B2 and the robot is in your hand, you should see as you press and hold button B2 down, your left motor starts to get faster and faster and faster. Okay, if you were to place that down on the desk, obviously the idea is to try and make it go in a straight line, but if you carried on pressing it down, then it would actually start turning off towards the right, I think it is. Okay, so we just want to use that to speed up the motor. Now, obviously, if the left motor is going too fast, we want to slow it down. So after we've done the check on button B2, and if button B2 is not pressed, we're then going to check is button B1 pressed. If button B1 is pressed, we're actually going to do the opposite. Okay, we're going to ensure that the motor is definitely running at least 50. Okay, because if you run below 50, it's going to be too slow. It's probably not going to move at all. Okay, and we don't want to do that. We want to make sure they are at least running a little bit. Okay, so we're going to check, is it definitely above 50? If it's above 50 on the speed, we're then going to decrease the speed by 1. Okay, so we're going to ever so slightly slow it down. Again, we're going to write to the EEPROM to ensure it's got the latest version of the settings in the EEPROM. Okay, and again, what you should now see, if you have the robot in your hands and you're pressing button B1, you should see that left motor gently slows down until it's nearly stopped, but it shouldn't stop because we've got that limit of 50 on there. So it should slow down to a very slow speed. Now the obviously idea here is that we're going to press the buttons B1 and B2. We're going to increase and decrease the speed of the left motor and try and match it to the right motor. We're going to place the robot down on the desk. If it veers off to either side, we're going to increase or decrease that speed on the left motor until it does drive in a straight line. Now at the bottom there, after we've done those 2 button checks, we're just going to make sure that the 2 motors are running with the current calibrated speed. That's what those 2 analog write commands are. We're just going to set in that left motor speed and the right motor speed to ensure they are correctly running at the speeds. Then we simply wait for 10 milliseconds just to give it a little bit of time. Otherwise, your button may react a bit too quickly, so it speeds up and slows down too quickly to help with your calibration. Okay, we can change that delay if we want to, but at the moment it's just a gentle delay. So that is it. That is basically the calibration process for the robot. What I want you to do is upload this code to your Arduino. Okay, if you want to, you can plug in the serial cable just to see the outputs. It might be useful, it might not be useful, but the key point of what we're going to do, hold the robot in your hands, okay? You're now going to have the two motors spinning as soon as you started this program. You're going to place the robot onto the desk, and you're going to see, does it drive in a straight line? If it doesn't drive in a straight line, okay, so let's say it starts to veer off towards the left, then I want you to increase the speed of the left motor to keep up with the right motor, okay? Again, press on button B2, that will speed up your left motor slightly. Press and release it a couple of times, place it down on the desk again, and see is it still veering off towards the left. Okay. The idea, like I say, is to try and get it driving in a straight line. If you now place it down and it starts to veer towards the right, okay, you're going to need to slow down the left motor by pressing B1. Okay. Basically, keep pressing these buttons and keep placing the robot on the desk. Be ready to catch it, obviously, because it's going to drive off. Okay, but make sure you keep pressing those buttons and try to calibrate it so that it goes at the same speed and more or less in a straight line. You might find with the wobbly desks and things like that, it very slightly veers off sometimes, but that's probably more to do with the desk than it is the motors. But you want it driving in more or less a straight line. It's all going to get saved onto that EEPROM in a future code that we write when we do our line sensing. Okay, we're going to add it in the code that actually loads from the EEPROM to pull your calibration in from the Arduino. Okay, so calibrate your motors, see how you get on. If you do have any problems, just let me know in the session. We'll have a look and we'll see if we can work out what's going on. It is writing out to the serial to say whether it's reading and writing successfully for the EEPROM. So if you do want to test that, or if you think that something might not be working, just plug in your USB cable and open up the serial monitor and see what it says on the serial monitor. It's a good way to help us debug. Other than that, like I say, any problems, just let me know in the session.